This week, we'll start where we left off. So we covered some facts about convergence, the monotone convergence theorem last time, and yeah, that was a very good thing because that allows us now to analyze convergence, issues of convergence, without having to identify a limit. So the next thing to do now is this is something that's a kind of a useful tool. I mentioned something about it last time, which should give you an intuition why this works. I mean, if not, it seems kind of like a strange thing, and how would I even think or come to think about this? But it's called the Cauchy condensation. Test, right? So what does it say? What does it say? So suppose we have a decreasing sequence of non-negative terms. So it satisfies that the bn's are all greater than or equal to 0 for all n in n. So all the elements in the sequence are non-negative. Then the series converges. The sum of the an's, n equals 1 to infinity, converges if and only if the sum of 2 to the n times b sub 2 to the n from n equals 0 to infinity converges. So one thing here is that this series here is made up of partial sums involving all the an's. This one only takes into account the also this is not an, this should be bn. For this particular theorem, we're considering a bn sequence. A sequence is called bn. Notation, yeah. So then, adding the bn's and obtaining a limit, and proving that it has a limit, will imply that this other sum, so just adding the b's for powers of 2, but with a weight, so 2 to the n, this is very large, this converges as well, and vice versa. So if we know that this series here converges, then we'll know that this other one will converge as well. So here what is the difference? Here we're adding all the bn's. Here we're adding only the powers of 2, the terms, the powers of 2 terms, and we're multiplying by a weight. So here we're adding fewer terms, but we're multiplying each one of those terms by a very large thing. And here, for this Cauchy condensation test to work, we really need that to use the fact that bn's are non-negative and the fact that the sequence is decreasing. If not, this will not work, and it will be become kind of apparent from the proof. So let's try to see. So we just do one implication. The other one is left as an exercise. But the idea is to compare terms. So I mean, we want to show that the partial sums. We're going to start assuming that this series converges. Then what happens is, if we spell out what the partial sums are, so the sum from n equals 1 to, say, 2 to the to the k plus 1 minus 1, say, of the bn's, this will be equal to b1 plus b2 plus b3 plus b4 plus b5 plus b6 plus b7, etc. up until b sub 2 to the k plus sorry plus b sub 2 to the k plus 1 minus 1. The minus 1 is down here. It does not cancel out this one. Is the subscript here. 2 to the k plus 1. All of that minus 1 to be that. And what is the idea here? So b1 is naturally less than or equal to b1. If we add these two terms, given that the sequence is decreasing, this is going to be less than or equal to 2 times b2. So 2 times b2, because b2 is greater than or equal to b3. Now b4 is the bigger of all of these four terms. So we might as well be adding b4 plus b4 plus b4 plus b4. And that would give us a bigger number. But then that would be 4 times b4, and etc. Until all these terms here can be bounded from above by 2 times, 2 to the k. This is how many of these terms are. And the first one, which is the biggest one, so b sub 2 to the k. Okay, and this is exactly the sum of from n equals 0 up to k of 2 to the n times b sub 2 to the n. And of course, since this is convergent, this is bounded from above. Because by assumption, remember we're assuming that this sum here converges. So because we are assuming converges. Alright, so the thing is now that, well, remember that when we started discussing convergence, we derived some properties of convergent sequences, and one of them was that if you had a convergent sequence, then it must be bounded. Not all bounded sequences are necessarily convergent. We already had a discussion about it, but every convergent sequence must be bounded. Okay, so So since we're assuming that this sequence converges, then we have that it's bounded. But we're gonna use that in order to show that these partial sums then are bounded. And so this is going to be called, say, well, okay, we're not going to call it anything. So let's try now that we're getting more comfortable with these kinds of arguments, let's try to do it in our heads and try to complete the details. So here what I'm telling you is that this M, which is independent of anything, this is just a bound for the convergent sequence made out of the partial sums here. We know that this series is convergent, so we know that it must be bounded. Well, the partial sums must be bounded. But now look at this on the left hand side. So this is the partial sum corresponding to for the original series up to, so we're adding the terms up to 2 to the k plus 1 minus 1. Minus 1 down here, of course. Let's roll that minus 1. It's not part of the exponent. So we're adding 2 to the k plus 1, all of that minus 1. So those are all the terms that we're adding. And the thing is that any partial sum can be bounded by a partial sum of this form. You just need to let k be bigger. So you always, so it's like the same thing by a number. If you have a number n, then that number is going to be less than or equal to some power of 2. In particular, 2 to the n. In fact, if you just consider the sum the partial sum sk, that's going to be bounded by this partial sum. Why? Because we have, and this is what I said at the beginning, we have non-negative terms. So whenever we look at the partial sums, with larger k, we're adding more terms, and so the partial sums become bigger, or at least they don't decrease. So it's not decreasing as a sequence. And so what we've shown is that all the partial sums are bounded. All the partial sums are bounded by m. And as I said, because we're only adding non-negative terms, then the partial sums constitute a monotone sequence. Monotone sequence, bounded, we can use the monotone convergence theorem, so we can conclude thanks to the monotone convergence theorem, right over here, I think it's better. Theorem that the sum from n equals 1 to infinity of the Bn converges. Okay, so we did one implication, so we started from this series. We assumed that this series converged, and we proved that this other one converged as well. What about the other implication? So assuming this converges, how do we show that this converges as well? So the idea is kind of similar. So here, here we use the bound for this convergent sequence of partial sums to deduce a bound for the partial sequence, for the sequence of partial sums for the Bn's. We can also do that. We can start from the bound for the partial sums of the Bn's and obtain a bound for the partial sums of the 2 to the k of b times b to the times b sub 2 to the k sequence. So the sequence whose terms are 2 to the k times b times b sub 2 to the k. And how do we do that? Of course, I mean, this inequality here is not going to look the same. But what we can say here, I mean, we can miss a factor of 2. So this, you know that this will converge if and only if the sequence b2 plus 2 times b4 times 4 times b8 converges. So this sum here will converge if and only if when we divide by 2, we still have a convergent series, right? But of course, if you think of b2, b2 is bounded by b1, right? So b2 is bounded by b1. Now, b4, remember that the b's are decreasing. I told you this was a very crucial thing. Is bounded by b2 plus b3. b2 and b3, they're both greater than or equal to b4. And if you do the same thing for b8, that's less than or equal to b4 plus b5 plus b6 plus b7. And you see what's going on now. So now we do the same thing with all the other terms. And what you have here is if we add everything on this side, this is, I mean, you have to write this down rigorously, but you see where I'm going now. So on this side, I would get the sum of the bn's. I'm adding b1 plus b2 plus b3 plus b4 plus b5 plus b6 plus b7. And on the other side, I will get the sum of two to the k minus 1 times b sub 2 to the k. You see, b2 is multiplying 1, b4 is multiplying 2, which is 2, so 4 is 2 to 2 squared, but here we have 2 to the 1, and here we have 2 squared times 2 cubed, to be 8, so 8 is 2 cubed. So this is the sum we have on this side. So this is, again, you have to do this rigorously, just like we did before for this implication here, just fixing a certain k and then bounding things in the appropriate way. And then once you obtain the right bound, you use the monotone convergence theorem. But here this looks pretty much like what we want, except that we're missing here a factor of 2 and we're missing a 1. But then you see that if we multiply both sides by 2, we get the sum from k equals 1 to infinity times 2 to the k b 2 to the k is less than or equal to 2 times sum equals 1 to infinity bn, n equals 1 to infinity of bn's. And if we add b1 is a given number, so that doesn't affect convergence at all. We're going to have that, well, b1 is the same as b1 times 2 to the 0. So we can put this back into this sum, and you can incorporate it in here, and we get that this here on the left hand side converges because we are adding a number b1 plus 2 times something that we know converges, something we know it's finite. Okay, so that's how we show that the other implication. So I'll leave you to complete the details of this. And now I am gonna give you a series of things that you should try to do on your own. I mean, besides the exercises and the homework, but I told you before that as we progress in our attempts to understand analysis and these kinds of proofs, you start doing more things on your own. Once you understand the idea, so we go slowly at first, more slowly at first, then later on, because we already, hopefully by then we already become accustomed to using these kinds of arguments. So corollary 2.4.7 is going to be left to you as an exercise. So I'm going to assume that you are able to follow what the book does. All these things, as we need to move on with the material, I'm going to give you some problems to work on from the exercises for this section. So this is going to be part of your next homework. And now we move on to the next topic, which is subsequences. And the Bolzano Weierstrass theorem. Okay, as I said, we need to start moving a little bit faster, so this is just a definition. So if an is the definition here of a subsequence is given in the book. This is definition 2.5. With 5.1, and it tells you that an, so if an is a sequence, so let an be a sequence, and a sequence of numbers n1, of natural numbers in 1 and 2 and 3, etc. Be an increasing sequence of natural numbers. Oh, I see a mistake. Sequence of natural numbers. Then, if you put all the, if you consider only the elements in the original sequence, coming from these subscripts, so n1 and 2 and 3, etc., that's called a subsequence. So a subsequence is a sequence in its own right, but the terms are terms that come from another sequence. So the sequence is a collection of numbers, but they're ordered in a certain way. So one comes before the next one, according to the n subscript here. So they keep the same order. And subsequence is an infinite collection of elements in the sequence. It could be the sequence itself, but the restriction here is that the order is preserved. So you have to pick infinitely many of them, of the elements in the original sequence, That's one thing. So AN, you pick one so from the ANs, you pick a collection of some of these ANs, and you put them in the same order as they appear in the original sequence. So if N1 is smaller than N2, then A sub N1 would have appeared before A sub N2. And so it must appear before A sub N2 in the subsequence. So you keep the order, and so these are the only two requirements. You have to pick infinitely many of these numbers here, and infinitely many subscripts. It's the same thing, and you put the elements of the subsequence in order, in the same order as they appear here, for the original sequence. This is the same thing as saying that you have an injective function from n to n, so the set of natural numbers, and you consider a sub phi n, and an injective and an increasing, so an increasing, strictly increasing function from n to n, then a sequence can be made at a sub phi of n, where phi is the injective one-to-one function from the natural numbers to the natural numbers. So that's it. So you can identify them both. I mean, you have a sequence of natural numbers. N1 is just some notation for phi of 1. This is phi of 2, phi of 3. So you have a phi, and of course, if so the function has to be, phi has to be increasing, and if the function is the identity, so N1 is just 1, and 2 is just 2, etc., then the subsequence is just the original sequence. Okay? But in general, we think of the sequences of being, the sequence would be made of some element in the original sequence. So in the book, they talk about, how they give you some examples of subsequences. Just to help you understand what we mean by subsequences and how they play a role when we're analyzing the convergence of a given sequence. But one thing that is very important is theorem 2.5.2, because of course subsequences, the behavior of subsequences depends strongly on the sequence, the sequence that they come from. So for instance, if you have a convergent sequence, then any subsequence must converge to the same limit as the original sequence. You cannot have subsequences converging to a different limit than the original sequence. If this were the case that this sequence is convergent. So subsequences of a convergent sequence converge to the same limit as the original sequence. I'm gonna leave the proof as an exercise, because it actually involves some ideas that we've used, and it's very short. So you should try to work it out on your own and then use the help of the book if you get stuck, or contact me. But in fact, it is related to the kind of questions I ask you about finding, say, a subsequence that doesn't have a bounded sequence, doesn't have a limit, and some particular example of those things where you are supposed to show by contradiction that a given a bounded sequence does not have a limit for a particular sequence. So the ideas involved are the same. And so yeah, so that's why I'm leaving it to you as an exercise. But the idea is, I mean, if I just want to summarize it, we assume that sequence actually converges to a limit L, and we give ourselves any subsequence. And then, of course, given any epsilon, since this since the subsequence, since the n and k's are increasing, you know that for the original sequence, beyond a certain point, when the subscript is bigger than some n, then the sequence is going to be within with an epsilon in absolute value of the limit L. So you just need to make sure that for some uh, value of k, the subscripts n sub k are going to be bigger than that n. And that's always the case because, of course, since the sequence goes to infinity, the sequence of the nk's go to infinity. I mean, this is an increasing sequence. Then, in fact, n sub capital N, say the big N that you had, has to be greater than capital N. So that means that so this is what I mean. So this has to be greater than or equal to n. The n, the one appearing in the definition of convergence that you need to find for a given epsilon. And so if you call it n sub n, a new n naught, say, then yeah, you will have proved that the subsequence will converge to the same limit. Okay, so this new n0 will be the one you need to find for the original epsilon, or for the epsilon you're given. Okay, so then there are other exercises that I want you to go over with. I mean, later on I'll point out to them, I mean, some examples. But for now, the important thing to keep in mind, this is very useful for proofs, is that subsequences, I mean, if you have a subsequence of a converging sequence, that it must converge and it must converge to the same limit as the original sequence. That's the important thing. So our next stop will be the Bolzano-Weierstrass theorem, which just says that this is theorem 2.5.5, Bolzano-Weierstrass theorem. It simply says what I've been announcing for some time now, that every bounded sequence contains a convergent subsequence. Okay, so I will just, this is a consequence of the nested interval property. So I will also give this to you, the proof of this as an exercise. So I would like you to go over it and ask me if you have questions. But this will be, I mean, this proof in particular will be very useful for you in order to, I mean, to get more experience in proving statements involving sequences and convergence. This is a very good thing. It's not an easy proof, I would say. It's not, yeah, it's not the kind of routine proof that I'm leaving to use exercises. I've been leaving to for you to do as exercises in the past, but it will be very useful for you. I mean, this is actually a very good exercise, very good thing. And if you can just try to work it out, go over it. I mean, look at the book, and then come back and try to complete it if you get stuck and everything, and then try to reproduce everything from the beginning and trying to understand it in a way that makes sense to you. This will be, I mean, this will be very fruitful. Okay, so the proof will be, okay, as an exercise for you. Okay. As I said, of course, if you get stuck or you need more explanation, please don't hesitate to contact me. So So then the next time, I mean the next video, we'll start with the Cauchy criterion, which is something that I talked about before. It has to do with completeness, and which is equivalent to the least upper bound property, or the axiom of completeness, the nested interval property. There are many things that are kind of equivalent, but this is something that actually extends to more general topological spaces, I mean to metric spaces. The notion of a Cauchy sequence, and how, I mean, the most important thing for you to know is that all convergent sequences will be Cauchy sequences, but Cauchy sequences need not be convergent sequences unless the space you're in is complete. And being complete just means that Cauchy sequences converge. So that's it. So that's for the next video. See you soon.